Calculus, video 78, use substitution with cosine squared x and sine squared x. So these end up being very useful for us, and because we often need to integrate cosine squared of x and sine squared of x, right? This sort of integral sine squared of x dx, it just comes up a lot, right? Same thing with the integral of cosine squared of x. They just happen frequently. And so understanding how to integrate them without having to think about it every time ends up being, very useful. In order to do so, we're going to have to recall a few trig identities. So we need to remember our trig. There are certain identities in trig that you should just know. You should know that the sine squared of x plus cosine squared of x is always equal to 1. It's a Pythagorean identity. You should know that. And you should be able to rearrange it to say things like sine squared of x is 1 minus cosine squared of x. There are others, right? Other identities you should know are what are called the double angle identities. And that's where we're going to start here. Double angle identities. We should know these, especially for sine and cosine. Right? We should know that the sine of twice an angle can be found by 2 sine of that angle cosine of that angle. That is a trig identity that we just need to know. A couple more. We should know that the cosine of twice an angle actually has 3 identities. One of them is cosine squared of x minus sine squared of x. Be careful, not cosine squared of x plus sine squared of x. That would just be 1, always. The cosine squared of x minus sine squared of x. Or, if you replace, say, sine squared of x with 1 minus cosine squared of x from that Pythagorean identity earlier, you end up with this. You get cosine of twice an angle, cosine 2x, is equal to 2 cosine squared of x minus 1. And then if you replace cosine squared of x with 1 minus sine squared of x, you get the third one. Cosine 2x is 1 minus 2 sine squared of x. Those are the double angle identities. You should know those. You need to go back and remember them and learn them and kind of walk through the process there. We got those double angle identities using the sum and difference formulas. The sine of a plus b, if you remember, is sine a cosine b plus sine b cosine a. And for the double angles, instead of a plus b, we did a plus a. So like sine of a plus a, that's the same thing as sine of 2a, which is, if you just plug in a's for all the a's and b's, you get sine a cosine a plus sine a cosine a, which is equal to 2 sine a's cosine a's. And so that's how we end up developing those double angle formulas, is from those sum and difference identities. You should take the time, go back and try that with cosine 2x, right? Or cosine 2a. Cosine of a plus b, and then make it cosine of a plus a, and walk through that sum and difference in order to get to the double angle. But our focus today is a little bit beyond that. We're going to take these 2 double angles right here. We're going to focus on cosine of 2x is equal to 2 cosine squared of x minus 1, and cosine 2x is equal to 1 minus 2 sine squared of x. And the reason we're focusing on those two is because they have, in this case, a cosine squared of x, which is what I'd like to solve for, and a sine squared of x, which is what I would like to solve for. So we're going to do them one at a time. Right, so we have cosine of 2x is equal to 2 cosine squared of x minus 1. And then here in a minute we'll look at this one. Cosine 2x is equal to 1 minus 2 sine squared of x. And we're just going to try to solve, on the one on the left here, try to solve for cosine squared. Get that all by itself. Well, in order to solve for cosine squared, I have 2 cosine squared of x minus 1, so I'm going to add 1 to both sides. So I have cosine 2x plus 1 equals 2 cosine squared of x. And then just divide by 2. So I get 1/2, dividing by both sides by 2 here, cosine 2x plus 1 is equal to cosine squared of x. And that's it. I've solved for cosine squared of x. Cosine squared of x can be rewritten as 1/2 times cosine of 2x plus 1. Please don't try to distribute that 1/2 and say that 1/2 times cosine of 2x is just cosine x. The 1/2 coefficient does not cancel with the inside 2x there. That angle, cosine of the angle 2x. So we're just going to leave it like this for now. So big star on that one. And on the right hand side, it's going to look the same. I have cosine 2x is equal to 1 minus 2 sine squared of x. I would like to solve for just the sine squared of x. So the first thing I'm going to do is subtract 1 from both sides. Cosine 2x minus 1 is negative 2 sine squared of x. And then, to solve for sine squared of x, we're going to divide by negative 2. Same as multiplying by negative 1/2. Negative 1/2 cosine 2x minus 1 is now equal to sine squared of x, which is good, but I'm going to go ahead and distribute the negative 1/2, or at least the negative sign. So instead of negative 1/2 cosine 2x minus 1, I'm going to distribute the negative sign and do positive 1/2. So I'll have sine squared of x is positive 1/2. And then instead of cosine 2x, it'll be negative cosine 2x. Instead of negative 1, it'll be positive 1. And so I'll write it like this: 1 minus cosine 2x. So sine squared of x is equal to 1/2 times 1 minus cosine 2x. Make that a little bit nicer here. Put a big star by that one. Okay. These are the identities that we need to know in order to integrate cosine squared of x and sine squared of x. These are often called the power reducing formula. And the reason they are called power reducing is we're taking a cosine function or a sine function. Let's stick with cosine for a minute. A cosine that's squared, so to the power of 2, and reducing it down where my cosine function now is just to the power of 1. It's of 2x, but it's only to the first power. And the reason we're doing this is because I know what the integral of cosine of x is. Right? The integral of cosine of x is sine of x plus c. I do not know what the integral of cosine squared of x is. So if I can reduce cosine squared down into just cosine to the first power, even if I have to do cosine 2x, that's okay, because I can find that integral with a u substitution. So we know that. We don't know this one, right? So we try to force it into a cosine of the power of 1. We want to have a power reducing formula for that. So let's try an example. We're going to use those two stars. I'll just do one. So for example, let's do the integral of 4 cosine squared of x dx. Okay, it's not a u substitution yet. It will be. We will use u substitution, but the first thing we're going to do is to rewrite this using the power reducing formula. So we're going to rewrite using the power reducing formula. Okay, I'm going to bring the 4 out front here. So I have 4 times the integral. Cosine squared of x right here, is equal to 1/2 times, parentheses, cosine 2x plus 1. 1/2 cosine 2x plus 1 dx. Okay, that's not a u substitution. That is simply an identity, right? Cosine squared of x is equal to cosine 2x plus 1 times 1/2. In my case, 4 times 1/2 is 2, so I get 2 integral cosine 2x plus 1 dx. Now I know what the integral of cosine of x is, but I'm not sure exactly what the integral of cosine 2x is. That's kind of complicated, and so basically anytime I have a trig function of something, and that something is not just x, right? In this case it's 2x, I'm going to do a u substitution for whatever that function is. And so I'm going to let u equal 2x. However, I'm perfectly happy just integrating the 1. with respect to x. I don't need to do a u substitution to integrate 1. The integral of 1 is just x. So what I'm going to do here, we haven't seen much of this before, is I'm going to split this integral into two integrals. All right, the first integral is going to be 2 integral cosine 2x dx. And then plus 2 integral 1 dx. And the reason I'm splitting this up is the one on the right here, I don't need a u substitution to solve. So I'm splitting it off of the one I do need a u substitution because I can integrate 2 integral of 1 dx. It's just 2x plus c. Right, done. So I'm going to leave that one, and it's just going to write it 2 integral dx for every step. This one, I do need a u substitution. On the left over here, I need a u sub. Right, I need a u sub to solve for this one. So I split it into 2. I'll do a u substitution, but only on the one on the left. The one on the right is just going to hang out. Okay, it looks something like this. Let u equal 2x. That inside of the cosine function. Du then is equal to 2 dx, and dx is du over 2. Doing my substitution on that first integral, I get 2 integral. It's now cosine of u instead of cosine 2x, and dx becomes du over 2. And then this one, I'm going to leave it just x's. 2 integral of 1 dx. The 2's happen to cancel in this case, but not on the one on the right. And so I get the integral of cosine of u du plus 2 integral dx, or 1 dx is fine. So that's okay. I have 2 separate integrals. One of them is with u's, one of them is with x's. Because I'm doing indefinite integrals here, that means I'm going to go back into changing everything back into x's at the end. But right now, the antiderivative of cosine u, that is sine u. Because the derivative of sine is cosine, so the antiderivative of cosine is sine. And the antiderivative of 2 integral dx is 2x. And then I only need one constant, even though I have 2 separate integrals because plus c at the end there. And then replace my u with 2x right there. And we end up with this. We have the sine of 2x plus 2x plus c. Remember that anytime you're doing an indefinite integral, you have to go back and substitute the u for what it was equal to in terms of x. You can't just change the bounds because there are no bounds. Okay, very good. Let's do one more. Let's do one with sine squared now. Okay, and let's do a definite integral. So how about the integral from, say, 0 to pi over 4 of 2 sine squared of x dx. Right. Before we do a u substitution or anything like that, we're going to use the trig identity, and it was this. The sine squared of x is equal to 1/2 1 minus cosine 2x. They're honestly almost the exact same formulas, right? For the cosine, remember it was cosine squared of x is equal to 1/2 1 plus cosine 2x. The only difference here is with the cosine squared you get a plus, with the sine squared you get a minus. Okay, so we're going to replace this with the integral from 0 to pi over 4 of 2 times 1/2 1 minus cosine 2x dx. We see that the 2 and 1/2 cancel out, and so we have the integral from 0 to pi over 4 of 1 minus cosine 2x dx. And once again, I can integrate 1 all day long. The integral of 1 is just x. I don't know how to integrate the cosine of 2x. I mean, I do, and you will too. You'll kind of, without having to do a u substitution, eventually you'll just know, oh, well, that's just sine of 2x over 2, right? And we'll get there. And you kind of saw that up here, that the integral, we end up dividing by 2 here when I solve for dx. U is 2x, du is 2 dx, therefore dx is du over 2. You end up getting that divided by 2 in there. Okay, we're going to see that here as well, where eventually when you integrate cosine of 2x, you'll just know, oh, well, that's just sine of 2x divided by 2. But for now, we'll continue on with the u substitution. But I want to separate this into 2 separate integrals. The first one, 0 to pi over 4 of 1 dx, I'm just going to leave, because I can integrate that, minus integral 0 pi over 4 cosine 2x dx. I'm going to do a u sub just on this one on the right. So we're going to let u equal 2x, du is 2, dx is du over 2. So again, the one on the left stays 0 pi over 4 of 1 dx, nothing happening there, minus integral, we're going to get the cosine of u instead of the cosine of 2x, and dx becomes du over 2, and I'm going to change my bounds. Okay, my bounds are going to change. Yeah, I didn't have bounds last time, this time I do. Bounds. So my old bounds were 0 to pi over 4. So when x was pi over 4, now u will be twice that, or pi over 2. And when x is 0, my lower bound, u will be twice that, which is still 0. So that's only going to go on the ones I'm doing the u substitution for. So I'm going to go from 0 to pi over 2 on these bounds here, because that's in terms of u, whereas the first integral stays in terms of x and is going to keep the x bounds. So we have the integral from 0 to pi over 4 of dx minus 1/2. I'm pulling this 2 out as a 1/2, this 2 in the denominator. Integral 0 to pi over 2 cosine u du. And now I can integrate. The integral of dx is just x, and I'm going to evaluate that from 0 to pi over 4. Minus 1/2. The integral of cosine of u is sine u. I'm going to evaluate that one from 0 to pi over 2. And so I get, plugging in the pi over 4 for the x and then the 0, I get pi over 4 minus 0 minus 1/2 times sine pi over 2 minus sine 0. Pi over 4 minus 0 is pi over 4, minus 1/2. Sine of pi over 2 is 1, and sine of 0 is 0. So I probably should have put that on there, 1 minus 0. And we get pi over 4 minus 1/2, which is a very fine answer. Or, if you'd like to put that in your calculator, pi divided by 4 minus 1/2 is about 0.29, somewhere about there. Okay, and that is how we integrate sine squared of x and cosine squared of x.